Okay, so this talk is about antenna modeling. So the first thing you might ask is, why should I do that? Why do I want to bother? Well, one of the things is you can kind of study a new design of a new antenna before you actually build it. You can kind of try, what happens if I string it instead of to that tree, to this tree? What happens if I raise it? What happens if I kind of have the legs go out different directions? So you can kind of do all those things without actually having to handle wires and trees and heat and whatever. You can also use it to find, given a particular design, how can I optimize it in whatever I want? Like, do I want to optimize it for the best performance in a particular section of a band or some other characteristic of the antenna? You can also look at an existing antenna and kind of see, okay, given the antenna, what would happen if I made some modifications to it? And you can kind of, without having to go out and make measurements, you can kind of, in the computer, see what would the SWR look like, what would the impedance of the antenna versus various frequencies, what might the pattern be like? And even if you then go out and do all these measurements, the idea is that the modeling has given you some idea what to expect. So if your measurements don't agree at all with the model, doesn't necessarily mean your measurements are wrong, but it gives you something to kind of ask, why are they different? Is there something about the antenna in the real world that the model isn't showing? And finally, it is not a learn a new skill, it should be learn a new skill. So let me give you a little background. The physics behind how an antenna works is pretty straightforward. You have currents running in a wire, alternating current running in a wire. It generates an electric and magnetic fields that expand out from the wire. And so in that sense, it's very simple. But when you start getting into, wires in the real world, wires with other wires nearby, the calculations become computationally very difficult. And it wasn't until about, I would say, the 1960s where you could actually write out the equations and then have a computer solve them. And up until then, the computers weren't really up to the job. To give you a scale of how those computers were, in the middle 1960s, I worked on what was at the time the fastest computer in the world. It was the 1965 supercomputer. That computer was about 1/20th the computing power of a Raspberry Pi, not even close to what your laptop can do. So the idea is now that as computing power became available, this became at least feasible to do. And of course, the people that were particularly interested in this were the military, who are often designing antennas for a variety of things, ships and planes and whatever. And so Lawrence Livermore National Lab, which does a variety of secret military work, developed a computer program that actually did solve the problem, and where you could input in some way the layout of an antenna or the pieces of an antenna, and it would still, it would compute the, things like the pattern and the frequency, SWR and whatever. The code for that is now, has been for quite a while, publicly available. So, since then, more recently, they've updated the code. So there's now an NEC4, which is also available, but you have to get a license because it's still, it's one of those things you can't export. So the trick here in modeling the antenna, and it's really simple, is you have to lay out, you have to describe to the program how your antenna, where are the lengths, where are the various pieces with respect to one another and with respect to ground. And then you have to tell it how you want to each wire, if you like, of the antenna has to be cut up into smaller pieces. That is not physically cut, but you have to describe it as a number of small segments, and the computer calculates the field from each segment, adds them all up, and gives you the result. So this segmentation, the reason I mention is because one of the things you'll need to know when you actually go to the computer to lay out an antenna, which we'll get to in a minute. So one of the problems with the NEC2 code it was written in Fortran, and there's nothing wrong with Fortran. It's still around. It's older than many of us. It has been around since the 1950s and is still in use. But the problem is it was written for Fortran in the days when input was on punched cards, which were 80 characters wide, and line printer output, which was 120 characters wide. And so you could use NEC2 in its original form, but you would have to be very careful about setting up your input so it all in particular columns, and it was easy to make a mistake and it was a pain. And so some people said, well, I could write a program that would let me, on some kind of graphical way, describe my antenna, and then it would translate it into the format that the NEC code wants, and then run the NEC code, capture the output, and display it back in a way that's friendly. So a lot of people have done this. And you can get these programs, just a couple. One of them that is touted a lot is something called EasyNEC. It's supported by the ARRL. If you get, I'm not sure about the handbook, but if you get the antenna book, you get a limited free version of it. It's limited in the sense that it won't let you just put up a very complex antenna, but at least it lets you do some very simple things. It turns out probably not much more than getting used to the idea of how you use the program. The full-blown version of the program costs money. And it's licensed by it's available if you want to look it up on ARRL. I think they actually will sell it to you. There are a lot of free programs. The one I use is called 4NEC2. It's available, there's a URL. If you just do a Google lookup 4NEC2, it will take you right to the page. This is, I like this one. It's got a lot of nice features to it, as you'll see. There are some others you can kind of, if you don't like this, you can kind of, you can at least start with this and then, branch out as you kind of get more experience. So one thing for reference, if you are an ARRL member, you can go to the ARRL website, and there are archives for QST, and basically I believe it's every article that was ever printed in QST is available in the archives, and you can look it up by month, by call, by whatever. There were a series of articles, and you can actually go on there's a URL right here on the slide, arrl.org/antenna-modeling, and it will take you to a site that on their website that describes antenna modeling and gives you pointers to the articles by L.B. Seebeck, who was a longtime antenna expert, wrote a lot of good stuff about antennas for many years. LB is now a silent key, but a lot of his writings are still around and they're really worth doing. There are also other tutorials. There's specific tutorials on antenna modeling in general, as well as antenna modeling for special cases like, how do I model a helical antenna? Now you say, well, why would I do that? Well, if you're doing UHF or VHF, work, that's a kind of antenna you might be wanting to design. So there are, the web is your friend in this case. So But if you want a more comprehensive introduction, I recommend the articles, the CBIC articles, highly. Okay, so here's what we have to do. I'm gonna in a minute. I'm gonna do the program, and we'll go through and model some antennas. So what we're going to do is have to lay out the geometry, that is where are the ends of the wires, and in terms of some, you think of it as north, south, east, west, and height, how high above ground. And there may be more than one wire, so we have to lay them all out. The coordinate system that all these programs use is an XYZ coordinate system, where Z is the height above ground, X and Y are two other directions, you know, on the ground. You can think of north and east or whatever. They're actually arbitrary. There's nothing in the program that is actually tied to a specific geography. So I always just, I don't worry about that. You know, if you're saying, well, I want my antenna pointing northeast, don't worry about that. Just set it up, you know, to point in one direction, and you can kind of see what the pattern will be like. And that can be, you know, whatever direction your antenna is actually set up as. So here's just an XYZ, just to remind you what they look like. And I have some conventions, because it's always nice to kind of make your life simple. So one of the things I do is that if all possible, I leave my antenna elements parallel to the Y-axis. So that is, a simple dipole will be firing along the plus or minus X-axis. We also try and center the elements on the X-axis, so they're symmetrical about that axis. So this goes from plus Y to minus Y. It makes it easier to enter your data, and it makes it easier to see your output. These are nothing special about these conventions. You can center them on, it's nice to center them on one of the axes. So I'm going to go now to Fornec 2. So I have to stop the share and go. Okay, so when you start up, when you start up the program, I'm getting some windows here. A bunch of stuff opens up, and one of them is this is the main screen. And what it does is it opens up to whatever you were doing last. What I was doing last was doing a simple example. I always think when you're doing these things, take something that you know what it does and model it, and that way you get it. You know, if the program doesn't behave the way you know the antenna should, then you've made some mistake. So I took about as simple an antenna as you could imagine, which is a simple dipole cut for 40 meters. And so let me show you what the input to this looks like. So this is the file in which it's like a little spreadsheet. It has a line for each wire. In this case, it is one wire. It has a number. The wires are all numbered. This is wire number 1. I've cut it up into 15 segments, which is you don't want the segments too big, and you don't want them too small. 15 was a good number for here. And it's going to have an X value of 0, a Y value of minus 33.5. The units here are feet, and it's 20 feet above ground. And the other end of the wire is also at X equals 0, but its Y is at 33.5, and it's also 20 feet above ground, and it's made of number 14 wire. Now, if you had aluminum pipe, for example, you would put a number in here for the radius of the, so that's the way you input. And the other thing is there is a source right in the middle of the antenna, just a voltage source. So here's one thing. Here's a description of what the antenna looks like. You can see kind of looking from above. It's a simple dipole. You can see it's parallel to the Y-axis. You expect to see the pattern looks something like a figure 8 pointing this way. So let's ask NEC to model this. So what I want to do is do a calculation. And so let's see, so it gives me some options. So let me do a frequency sweep. So I'm going to do a sweep, start at 3 megahertz, stop at 30, and with a step of 1/4 megahertz. So this is a kind of broad sweep to see what the antenna looks like. So I go generate, it's taking the files, it's sending them off to NEC. And there is the output. So so the output, here's a plot and it's showing you the pattern. This antenna is pretty low in terms of wavelengths. So you get a pattern, pretty much what you expect, something like this. I'll show you the pattern more horizontal as well. And you can see here's the resonance curve. It's resonant at 7. And again, around 22, which is about what you expect for a 40-meter dipole. It kind of works also on as a third harmonic on 15 meters too. This is kind of crude. I could, for example, zero in on just the smaller part of the curve. But one of the other things, so this is an SWR plot. Now, you can also look at the impedance plot, and that's a busy graph. But what this graph is showing, the blue curve is showing the resistance of the antenna as it over frequency, and the red curve shows the complex part, the impedance. And you can see right here at 7, the impedance crosses 0, which is what means to be resonant. And at that point, I can't get it quite at the exact resonant, but you can see it's 7 megahertz. It's got 26 ohms of negative, so it's slightly capacitive, and it's got 63 ohm resistance and the SWR. And now notice this, if I switch plays, it remembers where to put the cursor. It's got a 1.7 SWR, so that's not bad. Obviously, I would like to move this a little higher. And I do that by going back into the geometry window and clipping a little wire by just changing those numbers. Now, so one of the other things you say, what's the pattern of this dipole? So we want to calculate that. So here I go to far field pattern, and it's going to do it at the frequency 7.1. And that's the pattern, but there's a window, this 3D viewer, it's going to come up. Now, for reasons that I do not understand, this thing hides the pattern as its default when it comes up. But if I just show the pattern, that's what the pattern of the antenna looks like. Okay, you can see it's kind of elongated. It tends to fire along the x-axis. A lot of the radiation is going pretty straight up, which is why this thing is great for talking across the peninsula, but not so great for talking to Europe. So let me just show you a simple thing. You say, well, gee, you know, I just came into some money and I put up an 80-foot tower. What happened if I stuck this antenna up at 80 feet? So let's go change that. So let's change the height from 20 to 80. That's kind of, let me now actually calculate the pattern directly. So I go back here, calculate, far field pattern. And you can see the pattern is, you've got a lot more energy going out here, and you notice it's coming out at a lower angle, which is what you expect, having, you know, raised the antenna now to a reasonable height for a 40-meter dipole. and we can look at the and you see now the pattern is kind of a lot more energy is coming out, going in the direction you want, and it's also going at a low angle, which is good for propagation. So that's a simple kind of thing. So what more could I do at this point? For example, I could say, what happened if I made it into an inverted V, or I had it fed it off center. I mean, you can just start with this basic stuff and do a whole bunch of whatever comes to mind. All of this as without having to spend a lot of time out in the sun or wrestling with wires. Okay, so let's see what else we got. Okay, so here's an antenna. This is a more complicated one. I think it was about 2 years ago, I wrote an article for QEX. And the basic idea, I think I may have even given a talk I gave a talk at one of the tech cons. The idea here was that normally we think of an antenna like you want to make a dipole that was worked on 2 bands. You put in traps so that you would cut off the outside ends, so the inner part of the antenna was at the higher band and the outer part of the antenna worked on the lower band. I said, you could a trap actually behaves like a capacitor at low frequencies and an inductor at high frequencies. And so if you had an antenna that was a little bit short on the lower frequency, a little bit long on the higher frequency, the trap would actually do that, and you would use the whole antenna rather than just parts of it. And so I went through the article, talked about how you actually calculated where to put the trap and what values of L and C you had to make it with. So this is a model I did. So this is a model of the antenna. It's
And Dave, sorry to interrupt. We can only see the main input window. If you have another graph or a screen or whatever.
That one. Can you see it now?
No, it's only one screen at a time.
Oh.
So we're seeing the main window, like the calculations window.
Oh. You haven't seen any of these other graphs?
No, sorry to interrupt.
Oh. You should stop me sooner. Let me go back then. So let's see. I've got to share the screen. I can't share more than one.
No, just one screen at a time, unless you can put it all on one screen.
I mean, it's just the whole desktop is what I want to show.
Right, yeah, you should see the whole desktop, but we're only seeing the calculations and not any graphs or anything.
It isn't showing me as an option the whole desktop. Oh, here we go. Well, okay, so here's the antenna I'm talking about.
Yeah, there we go.
So you can see it's these little dots here represent the traps. Okay, this is going to be a little awkward, but Okay, so this is a more complicated layout. So I've got it basically have 4 wires. The antenna, each half of the antenna is a wire that goes from the center to the trap, and then there's a wire that goes from the trap to the end. So here's the wire I'm going to start at one end. This antenna I've modeled at 30 feet above ground. So I'm starting at a Y of minus 20 feet. And I'm going to Y minus 20 to minus, so there's 5 feet. And then there's going to be a trap. And then the next piece goes from minus 15 to 0. And then on the other side, it's the same thing. It goes from 0 out to 15, and then from 15 to 20. And over here, I have 2 traps. First trap goes in wire number 1 in the first segment, at the end of wire number 1, that's segment 5. And the other one goes in wire number 4 at the end also. So, and these are values that I had calculated from the paper. So, okie dokie, let's see. Okay, I'll have to switch. So this is what the antenna looks like. That's the geometry model. You can see it's got a wire from the end to the trap, from the trap to the center, and the same outside. Okay, so whoop. So I'm going to come over here to the main screen. I'm going to say I want to do a calculation. And I want to generate some output data. What I'd like to see here is a frequency sweep. I don't need to start at 3. I'm going to start about 5 and this is only going to go to, it's supposed to go only 20, so I'll go to 15. And I can make the steps a little smaller. So I'm going to generate. The computer will sit here for a while. Okay, now I have to. And this is the output. It shows, this is the SWR curve. It shows you, that here it is resonant, and there it comes down again, and it's resonant. So this is antenna that was 50 feet wide. It's too short for 40, way too long for 20. But you see, the traps have made it work at both bands. And the other thing, this graph, I guess I said this, I didn't realize you weren't seeing it. You can also look at the impedance of the antenna. This is the resistance with versus frequency, and this is the reactive component. And you can see right here about this is close to the resonant point. So let's see what else now. So one of the things I'd like to do is look at the pattern of the antenna. Let me go back. So here I'm going to ask it, I want to calculate output data. And this time I want the far field pattern. It's going to do it at frequency. I'm going to look at the far field pattern at 7 megahertz. Okay. And let me show you. So this is a nice 3D viewer showing the pattern. you can see it kind of looks like what you expect from a dipole. That is, there's a fair amount of the radiation that goes up, and it tends to be, looking at it from up above, you can see it tends to be more or less broadside to the antenna, but it's fairly wide. I mean, it's not unlike a regular dipole. So this is nice, way to view it. And you notice this viewer lets me kind of turn this around. If there were a more complicated pattern, you can kind of turn it to see. Sometimes there are lobes that go out in various places. At this point, maybe I should stop for a minute here and say, we have any questions at this point? I've dumped a lot of stuff on you fast. Maybe time for somebody to kind of any questions here? Stephen.
Sorry, I don't know why I unmuted. I didn't really have a question. Apologize.
No questions. Okay. John, K2LYV.
Don't forget, you can unmute yourselves if you have any questions.
No. Okay, no questions. So, Lee?
Would be resonant on. What band's your trombone resonant on?
It resonates somewhere between, I think, about 57 hertz, and on a good day, maybe about 500 hertz.
Oh, man. Go to the piano. Work the piano. That'll work for you.
Yeah,
all right.
That one has a slightly wider range.
Yeah.
Well, not much on the low end.
Yeah. I do have a question involving the traps. How are you deciding what resonant frequency for the trap?
That was the whole thing about the paper that I wrote, is that what I did is I said, basically when the antenna is too short, you want to put in some capacitance to make it effectively longer. And when the antenna is too long, you want to put in a little inductance. I mean, sorry, the other way around. You want to put a little inductance to make it effectively longer. And if it's too long, you want to put capacitance to shorten it. And so the trap does that. It switches over between its resonant frequency from one to the other. And what I did is I said, I know what frequencies I want. I know how much I need to correct at the lower frequency. And I know how much I need to correct at the higher frequency. And given those two numbers and the frequencies, I can then compute the resonant frequency of the trap and the values of the L and C.
Okay, so you're calculating the reactance first.
Yeah, I start with saying, what frequencies do I want this thing to work at? And so I think that's when I said I wanted it to work at 7.05 and 14.05. And then I said, given this antenna, that is the 50-foot dipole, how much inductance would I have to add, or capacitance would I have to add to make it resonant at each of those two frequencies, and then using that in the frequencies, and you can go read the paper, or I'll send you a copy. It tells you how to pick the trap. It basically gives you the two trap L and C values of the trap, and that determines its resonant frequency. And you can vary the position of the trap to try and make everything work as well as possible.
Okay, that makes sense. Moving the trap closer, the antenna gets smaller, but the trap has to provide more reactance.
Right. And what you really want to do is get the trap. Most of the radiation from an antenna is about the middle third. If you look at any of these things about the current distribution of the antenna, it kind of is zero at the ends and it peaks in the middle. And so most of the radiation occurs from the middle, about the middle third. And so you'd like the traps to be further out than that, so you get the beefy part of the antenna without any trapping or anything.
Okay, this makes sense to me now.
Yeah, it doesn't make any sense by itself. I mean, you had to know that it was the calculation was tricky.
Okay. All right, now I'm starting. Yeah, because I've read Al Buxton, W8NX. He's a silent key now. I read his work on building antennas that weren't naturally resonant at any one band, but by trap design, we're able to be space efficient yet resonate on multiple bands. And he uses a somewhat different technique where nothing appears resonant until you put it all together.
Yeah, I've read his papers. I have him. Buxton also did something which was unusual at the time, is he made the traps by winding coax on a form. And those coax traps were kind of a hot thing for a while. I don't think anybody does them much anymore, but the only problem with Buxton is he never explained how he calculated any of that. He would tell you, here's an antenna and wind the traps this way. And he had about 5 or 6 different antennas that that would do whatever, he had them for various combinations of bands and lengths and whatever. And they were supposedly pretty good antennas, but all you could do basically was copy his design. He didn't tell you how to design your own. And I do have somewhere his code. It's in BASIC, and it's basic spaghetti code, and I don't have the patience. Life is too short.
Yeah, including my life, your life, and everybody else online's life. I take it it's one of those that's just written linearly with nothing we could break down.
Well, you kind of have to spend a lot of time marking off the subroutines, and then you have to kind of convert what the basic is to something like algebra, and then you have to then figure out, okay, what is he doing? Why is he doing this? And it was a nice ad, but it had its limits.
Okay.
It didn't let you do anything on your own.
So we don't have that to work with either right now.
I mean, you could duplicate one of his antennas.
Mm-hmm.
I built one once just to see if I could do it. The traps are kind of weird. I just wound coax around a piece of PVC coupling, and you basically kind of tie the one end of the coax back to the shield at the other end, and so you have the center wire at one end and the shield at the other end as your two connections to the trap. And it looks weird, and you're saying, well, why are you just connecting the input back to the output? But you have to remember that the coax is coax behaves like, there's a phase shift.
Mm-hmm.
And also the outside of the coax is your coil.
So it behaves as a lumped impedance.
Well, yeah. And there were several papers arguing about how you model it, the impedance of it, the L versus C. So.
Yeah, I think I'm going to go back and look at some of his stuff, and I may email you for a copy of your paper.
Okay, I will send it to you.
I appreciate it, Dave. I've taken up quite a bit of everybody's time. I apologize, but I do have this curiosity.
One other thing, hang on, let me share it, go back. Hello? Oh.
Yeah, I was going to ask if you could show us that very first diagram that we missed on the simple dipole.
Yeah, I'm having trouble getting Zoom to behave here. I seem to be. For some reason, I'm going to have to log back into the meeting.
Let me try muting everyone, Dave. I don't know if that will help or not. Hold on.
No, I have somehow. Okay, I'm back. Okay. So there was a question, you wanted to see something?
Yeah, the very first diagram on the first example that you did for us. I guess I'm trying to visualize the segments that you described, and I really couldn't.
Let me go back there. Hang on, I'm opening stuff. Okay, can you see this now?
Yes, sir.
Okay, so this is a description of the wire. It's one wire. So it's got 15 segments. So the wire is 67 feet long. So each segment is about almost 4 feet. You want to make them small, but you don't need to make them tiny. You want them small compared to a wavelength. So here's the description. So here's this antenna is going along the y-axis. So its x coordinate is going to be 0 throughout. It's one end of it is at minus 33.5 feet. It's 20 feet off the ground. The other end is also at x equals 0, but it's at 33.5 feet positive, also 20 feet off the ground. And it's made of number 14 wire. Okay, is that?
Yes, sir. And so the segment division is not shown graphically. It's just plugged in the spreadsheet portion.
Right.
Okay.
You don't have to describe every segment. You're basically saying, here's a wire divided into a certain number of segments, and you want them typically, 15 maybe a little bit low. I'd probably go to somebody like 21 or 25. But one of the things is, of course, as you increase the number of segments, it takes more time to compute. So you're trading off your time for getting things more or less right.
Okay.
Okay. So here, since I'm sorry, I didn't realize you weren't seeing this. Here's the source tab, and you can see I have one voltage source. It's tag 1, meaning it's in wire number 1, and it's in segment number 8. So that's the middle of the wire.
Ah, okay.
And all I'm doing This will make it a 1-volt source at the center of the wire. It doesn't, you don't really care what the actual voltage is because you're really only interested in the relative performance.
Right.
One other thing that has tripped me up time and again, over here in this tab that says symbols, there's a little thing down here at the bottom that says scaling. 4-neck tends to come up in meters. And so you need to kind of click this on feet. You can also, I don't want to spend a lot of time on this, but you can also, for example, go back here where you're spending the geometry. I could put a symbol in here, like I call this minus length plus length. And over here on the symbol, I could say length equals something. Now, that may seem kind of, okay, on this example, that's kind of not worth very much. But if you have an antenna with 10 or 12 wires, changing the value of the symbol here is a lot better than changing it at 5 or 6 places, different places in the description. Another thing, and it wasn't appropriate for here, but you can actually ask 4-neck to optimize the antenna. So for example, I could give the ends of the antenna the definition of plus or minus length, define length here, and then there's a whole optimizer that you say vary length to make the SWR minimum at 7.05.
Oh.
And it will kind of run around doing all this stuff. It's really cool. So you can, there's a lot more in this. There's a lot more you can do here than I've talked about. I just wanted to give you, I mean, what I like to do, my intention in doing these things is to kind of expose you to something. And I'm a big believer in, go out and try it. What can you break?
Right.
It's not like climbing a tree and falling off a ladder. I mean, it gives you an added tool to kind of do things when, it's raining or too hot or whatever. And you can kind of ask yourself, if you have some weird geometry, for example, because you have a small yard or you have HOA, for example, you could ask yourself, how would I construct the dipole in my attic? And somewhere I actually have a couple of calculations where I tried that. And so that's a lot easier to spend some time doing that now, so that in, November, December, when you can actually go into your attic without killing yourself, you could then go up and put up an antenna. So it's a kind of useful tool. If you're into that kind of thing, I just always think it never hurts to hear about this stuff.
I appreciate that. I really do. I have more time than money, so this is right up my alley. It's
right. I mean, right now we have a lot more time than anything else, right? and I didn't get to be tech coordinator because I wasn't interested in the technology side. So I tend to kind of have this bias of, well, here are all these neat techie things you can do.
Right.
And, it's a great hobby because there are lots of different things, and technology is not the only thing people are interested in. Yeah. But I figure I might as well be I think they call it an evangelist for the technology side of the hobby. So this is just another nice tool to have. I like that it's free. So if you had to pay a lot of money for this, you wouldn't, if you had to pay $70 or $80 for the software, you wouldn't really want to do that unless you really wanted to do something.
Right.
This way, it's free, and you can say, I'll invest a couple hours in experimenting with this and see what I can do.
Right.
Remember, almost all these programs work off the same core computational engine, the NEC2 is doing all the actual computation. So they only differ in how you put the input in and what output it displays.
Okay.
There is another core computation engine. It's called MiniNEC. It was written back in, I think I would say probably the late 90s. When computers, laptops, or even desktops really couldn't handle the Fortran of the NEC code.
Mm-hmm.
And so people rewrote it in a way. And I'm just trusting the NEC code more. I mean, the people who did it were paid a lot of money to be experts in this stuff. And so I think, if anything, this has got the best implementation. I would think the interface is different, but that was a sign of the times. One of the things, okay, let me share this. Hang on. Okay, so this is the main window. If you do File here, you can obviously save file. This is my directory of things that antennas that I've modeled for one reason or another. But the program itself, this is the install directory for the program, and there's a little folder called models, and guess what's in there? And you can see just from the titles, you can kind of see, okay, all sorts of high frequency beams, collinears, multiband, short, simple, VHF, VH simple, VH. You can let me just open one at random. Here's HF beam. Oop, yeah, that one's empty. Uh-oh. Well, they moved. There's a huge, long set of files of examples. There are hundreds of them. So if you want to design something, you could, if you wanted to design, a 3-element Yagi, for example, somebody has already done the basic entering of stuff, and it's a lot easier sometimes to kind of alter somebody's
right
line than start from scratch. I'm sorry about that. I thought they were. They're here somewhere.
Mm-hmm.
I do most of my my modeling on. I have a separate computer that sits on my desk that does nothing but ham radio stuff, and its disk made that horrible clicking sound that says "I'm dying" on Saturday, and so I had to switch to this, which is just my other computer for everything else.
Yep.
And so I don't have necessarily the full. I haven't done a lot of modeling on this particular computer, so sorry about that. But
I understand.
Okay, anybody else? Well, if you want to try it, you can always find me K2LYV at ARRL.net, and you have any questions, I'm here. I'm not exactly, like everybody else. I'm just sitting here trying to stay safe. Dan?
I do have one question.
Yeah.
Yeah, I do have one question for you, if you have time.
Sure.
Is this beyond the scope of a like a lid appliance operator like myself, or is this something that's within the realm of someone with or do you need advanced technical skills to do this?
I would like to think that if you may, it's one of those things. If you find it interesting, it's not the kind of thing that you would have to have 3 years of advanced calculus or whatever. It's I think once you get the idea, it's you can think about what would you do if you went out in the yard and started stringing things up. You can essentially do the same thing here, and it's just a matter of practicing with it for a while. It's if you wanted to do really exotic things, well, none of us are really good enough antenna designers that we're going to look for the really exotic kind of things in antennas. But for just asking simple things like, if I made this dipole an inverted V or raise the height, what would it do? I think if you found it interesting, I think it's within the realm of quote simple appliance operators. I hope that's why I'd say yes. But
Cool. And anyone else have any questions? Just a reminder, we've got the virtual Talk Fest on Saturday, 8 to noon, programs and presentations, and we're going to try experimenting with selling stuff. You got stuff to sell, take a picture and put in your profile picture, and you can use the chat function while the program's going on. We think that's probably the easiest way, but this is one big giant experiment, so bear with us and hope to see you all on Saturday. That's about it, Dave, unless anyone's got any questions.
Hey guys, just to let you know, if you want to do a lot of this stuff and learn how to do it, Dan and Dave and anyone else, the ARRL antenna book comes with parts of this, a different program, but it's a similar program, and it's really easy to use.
It's very similar, but it has a big disadvantage is that you can't do much more than a simple dipole.
That's true, unless you buy the paid portion, but that's when this one's better.
The paid portion doesn't do anything that this doesn't do.
That's right.
And this one actually has better graphical displays than the it's newer.
I agree.
Right.
But I mean, if you got the antenna book, it comes with it, so that's a way to get started.
Yeah, you can practice with that, and then if you get into it, I would drop the EasyNet free version and try this or there are a couple of others. This is the most popular of them.
And the antenna book gives you the background, the chapter of background on how it's done and how it all works. It's very handy.
Yeah, you can model all sorts of things in this, including transmission lines, and there's a whole accessory. If you wanted to do something like model a parabola pounded out of sheet metal, this thing will actually let you design the parabola so that you can put the input into the program. It's got all sorts of features. I can't even figure out what I would do with it, but it's all there.
That's it. That's all I have.
Thank you, David. I really appreciate this. This is great. A lot of good information. Again, if you want to email David, you can do so at his call sign at arrl.net. And I have nothing else. Any other questions for Dave or anybody else?
No, by the way, this works really good through the relay through Facebook, because I watched the first maybe 40 minutes about this through Facebook, and it works really. I wanted to see how it worked, and it worked great. So if you don't have Zoom capability and you want to do it on Facebook, you can go there, do it there.
Very good. Dan, thank you for putting all this together, and hopefully we'll see you and hear you at TARC Zoom Fest this coming Saturday morning. Have a great evening.